Okay, welcome to lecture 22, closed conduit flow part 2. And today we're going to solve the three types of problems that use the Moody Diagram. This is like really cool, complicated stuff. And we're really kind of getting towards the apex of the difficulty level in this class. So pay attention, buckle up, and, let's just be ready to go. So right here, I have kind of shown what the three types are. And it's a little bit hazy if you stare at these. First thing that I kind of want to point out is that my font isn't very good. These V's are actually news, so that's the viscosity of the fluid, not the velocity of the fluid. So beyond that, at this point, you're staring at this, you're going, well, I can't really, what's the difference here? Okay, well, basically, it's which variable or do you not know. So in type 1, you don't know the head loss due to friction, the frictional losses. In type 2, you don't know the flow rate. Okay, and in type 3, you don't know the diameter of the pipe. Okay, and these go in kind of increasing difficulty. Type 3 is the worst. Okay, so this is the difficulty is kind of increasing in this direction. I can promise you on the test, on the exam, you will have one of type 2 or type 3. Can't say which one necessarily because I haven't made the test yet. I think in the past it's usually been a type 2, but again, it's all based on chance, so it could happen. So just, kind of be ready for that. All right, so I'm going to start this off, and we're going to look at this first problem. And I've already kind of lined up the tools for you, and there's some givens here. Okay, and so we're given the flow rate. We're given the length of the pipe. So that's from here down to here is about 50 feet. We know the viscosity of the fluid. This is the viscosity. I know it looks like a V. It's just my font's not very good. And this pipe is made of concrete. Okay, and so we're going to talk about where all this comes in. This is kind of our first time doing these things, so we're going to drive at that. And we want to know what the depth of the water needs to be to make this happen. Okay, and so you might be thinking, okay. So basically the way this works is the deeper this water is, the more pressure there is at the depth of it, and so the higher the velocity of it exiting the pipe. Okay, and so we're asking for the height when the flow rate is 10 CFS. Let's just pretend that's an F. CFS, okay? So what we're trying to figure out is, what is the depth that's going to give us 10 cubic feet per second if the pipe is made of concrete and the fluid has, this viscosity and the length of the pipe is so much, because in order to, so the energy on the left-hand side over here at point 1 versus the energy at 2. And basically what we know conceptually is that at point 1, we've just got this potential energy associated with the elevation. And all of that potential energy is going to be converted as it flows through here. It's going to be converted into velocity at 2, but some of it is going to be lost to head loss. Okay, so that's kind of what we're dealing with here. So looking at our tools, the most obvious one to use here is going to be the energy equation, among other reasons, because they tell us it's a concrete pipe. So they're asking us to deal with the fact that it's a concrete pipe. So how much energy are we going to lose? We're going to have to get into that. Okay, so we're going to start with this energy equation. And so there it is. And what we're going to do is, first I'm going to start by just getting rid of things that don't exist in this problem. So between 1 and 2, there's no pump. Between 1 and 2, there's no turbine. Between 1 and 2, there is a head loss, so we're going to have to deal with that. Okay, so at 1, the pressure is atmospheric. Okay, atmospheric. Okay, at 2, the pressure is atmospheric. Okay, at 1, if I make this our datum, okay, then Z1 is H, and Z2 is 0 because it's at the datum. And then V1 is going to be, we're going to make that 0 because of the tank or the Tahoe assumption. And then V2, well, we don't know what V2 is, right? And so then the last thing we need to deal with is this head loss term, which this head loss is going to be HF plus HL. Okay, and so we haven't dealt with this HL yet, this loss due to minor terms. And really that comes into play, really there's going to be like a little loss right here, okay? And we're the h lowercase l, that looks like a little e, but let's just pretend. Okay, and we are just going to ignore that for now. Okay, so what's nice here is a lot of the terms go away, and that's, you know, pretty typical for all this. And we're also going to pretend that this is an equal sign. Okay, because that's clearly a mistake. Okay, so what's nice is, you know, on the next step, we've got the potential energy due to elevation on the left, okay, is being converted into alpha V2 squared on 2g plus, okay, it's being converted into velocity plus this head loss, which is all in the term of friction, is all in frictional loss. Okay, so that's pretty cool. Okay, so that says, okay, well, obviously the next thing we need to do is we need to get at this, okay? Because we can get at the velocity pretty easily, I think. You know, we can get at the velocity through continuity, okay? And maybe we'll do that right now. Okay, get that out of the way. So let's go ahead and get that out of the way. Okay, so there it is. If we just kind of let it all happen in a split second. Okay, so we've got the V2. So the V2 is good. You know, we've done our continuity. We're in good shape. The next thing we need to do is we need to get at this HF. And the way we do that is with the Darcy-Weisbach equation. Okay. And so what that will do for us is it's going to let us kind of go in here and we can say, okay, well, I'm just going to replace the HF with the other side of the Darcy-Weisbach. So it's going to be alpha V2 squared. I'm going to leave it in symbols for now. Plus, so this is going to be F L on D V squared on 2G. Okay, and that's the velocity in the pipe, which is the same in along the whole length, so I'm just going to call it V2 so that we don't need to create a new variable. So what's nice is this kind of lines up pretty nice for us, right? So we can say H equals, well, we got to figure out the alpha. So let's just kind of zap and do that real quick. So if we calculate the Reynolds number right here, okay, so we can see that this number, the Reynolds number based on the velocity in the pipe, the diameter of the pipe, and the viscosity of the fluid in the pipe, we can show that this is turbulent so that so alpha then is equal to 1, okay, 1.0, okay? So if we go back over to our initial equation over here, we can say H equals, I'm going to say 1 plus FL on D V2 squared on 2G. Okay, so this equation basically is, you know, we're ready to go, except for the one problem. Okay, because we've got basically everything in here, except we don't know F. Okay, so the F is the problem. So the way we're going to deal with this is we're going to use the Moody diagram. So what we will do is we will scroll down here, and here is the Moody diagram. Okay, and the Moody diagram, of course, is not something that you're used to yet. So it's going to be potentially frustrating. And I want you to remember that from above, you know, we've calculated the Reynolds number, so that's along this x-axis. So 1.3 times 10 to the 6th. So here's our 10 to the 6th right here. This is 1 times 10 to the 6th. This is 2 times 10 to the 6th. This is 1.5, so 1.3 is maybe right in there. Okay, so if I wanted to, you know, kind of label that or, you know, prepare myself for what's coming, you know, maybe I take my ruler out and I, you know, draw a line right along here. Okay, so that we're kind of ready to go. Okay, now for the relative roughness, we've got a Ks over D. Okay, so our equation is epsilon equals Ks over D. So this is epsilon. Okay, as your book uses it, I will point out that there's a little discrepancy with how the FE equation guide uses epsilon. So we'll talk about that, but not right this second. Okay, so this Ks, this is the roughness of the pipe, and this D is the diameter of the pipe. So we know the diameter of the pipe is 1 foot, and the Ks this is a concrete pipe. So if we go over here, and this is out of your textbook, and if we look at a concrete pipe, okay, we are in the, what do you call it, system, the British system. And so concrete's kind of an annoying one because it's somewhere in this range, okay? Now, normally what I would recommend you do in this case is you pick one that's going to work out really nicely for you. If I were doing this again, I would choose 0.12 inches, because if I want to know how many feet that is, that's 0.01 feet, and that's going to plug in nice. However, unfortunately, whenever I did this the first time, I didn't choose that number. You can choose any number you want if I give you this. Normally, if I give you concrete or something like that on a test, I'm going to say concrete, I'm going to tell you what the KS is, because that's going to make my grading life easier. It'll also be less stressful for you, so you won't have to pick a number. For this particular problem, for whatever reason, I chose 0.015. Okay, so that number in inches, if we convert to feet, is 0.00125 inches. Feet. So, now why you would do that to yourself, or why I did that to myself, I don't know. But it just shows to go you why it pays to be a little bit more thoughtful. Okay, I mean, it's not really going to matter, but it's just, it just stinks when you do that. Okay, so if we're gonna take that number and we're gonna plug it in over here, 0.00125 feet. Okay, notice we've got feet over feet, so epsilon is unitless. Okay, it's 0.00125. Okay, if you're like me, you want to put that in scientific notation. It's a bad idea, because for whatever reason on these Moody diagrams, they never put it in scientific notation. They always put it like, in whatever, annoying units, the way they've done this. Okay, so we're going to find 0.00125. So here's 0.001, here's 0.002. So we're about a quarter of the way between those two. Okay, now this can get quite frustrating, especially if you get into the curvy parts of the graph. Looks like we're not quite going to get into the curvy part, but I'll just go ahead and draw it this way. Okay. Now you can imagine if we got into the curvy part, then this line is going to kind of follow along here, and you're just going to have to do the best you can do. Okay. But what's most important to us at this point is that, we've got this intersection right here. Okay. And so if I want to get F, the friction factor, we're just going to follow that point over. I wish it wouldn't keep resizing on me. We're just going to follow that point over until we get to the vertical axis on the left. Okay. So to the extent that I'm capable, to two significant digits, 0.021 is F. Okay. So that's how we use Moody. Okay. That's the easiest way to use Moody. It's going to get a little bit more complicated, but make sure you can do that. Try it a couple of times. We will end up with some that get on the curvy part, but we'll see. So to the best of my ability, that's the reading. And if I check my example, I ended up with the same number when I did it then too. So that's pretty good. Okay, so we can go back up here, and now we can attempt to solve this problem all the way. Okay, because what we're looking for is H. So we'll say H equals 1 plus 0.021. The length of the pipe is 50 feet. The diameter of the pipe is 1 foot. And then we've got V squared. V is 12.73, I believe. 12.73 feet per second squared on 2 times 32.2 feet per second squared. Okay? And so that's just a plug and chug. And we end up with H equals 5.14 feet. Okay. So that's it. These are the straightforward ones. This is a type 1. And I think that the one thing that's kind of weird about this is you might say, wait, that's a type 1. But, up here, when we said the 3 types of problems, you said we're looking for the head loss due to friction. Okay, and if I come down here, I don't see that. But the thing is that it boils down to when we began the problem, the initial thing was basically we ended up where the head loss due to friction, what we didn't know. And that was why we were able to do this. And it's really the most straightforward way. 2 and 3 are going to be more difficult. Okay, as I said, the difficulty goes up as you go down this list. Okay, so let's slide over and let's work on number 2. All right. So here we've got, and I brought the tools with us, water, viscosity. Okay, again, if you can't recognize that that's a viscosity, notice the unusual units. So that's a viscosity. Okay, water of a given viscosity flows through a 0.3 meter riveted steel pipe with a kind of so the KS, like what they call the sand roughness. Okay, now I'm doing this the best I can. This doesn't even come with a picture. Okay, so water flows through a 0.3 meter riveted steel pipe. So 0.3 meters, that's the diameter. Okay, and the fact that it's riveted steel has a KS of 3 millimeters. So that means from here to here is 3 millimeters, okay, or 0.003 meters, with a friction loss of 6 meters over a length of 300 meters, okay? Find Q. Okay, now whenever you're finding Q, Q can be very difficult because without Q you don't have V, okay? In this particular case, this is a really challenging problem, okay? So let's think about our tools. First of all, continuity. Well, we don't have Q. We do have an area, but we don't have Q. So it's going to be very difficult to use because we don't know, we could have area, but we don't have Q or V. So this is going to be, at least initially, out. Okay, geometry. Well, there's really not a whole lot going on there. Okay, maybe, not really much we can do. Hydrostatics. The fluid is moving everywhere. Okay, energy is a possibility. It seems highly likely because we've got a friction loss. And so we'll talk about that in a second. And then we've got momentum. Okay, and momentum, nothing in here says anything about forces with moving fluids. So momentum is out. Okay, now the energy equation is problematic, I think. Let's just, by the way, I'm not solving it yet. We're just going to kind of think about it. But let's imagine that I've got a point here, and I want to call this point 1, and I want to call this point 2. Say, okay, well, let's do some energy equations. So there's the energy equation, okay? And the pressure at 1 is unknown, and the pressure at 2 is unknown, but they're both in a pipe. Okay, Z1 and Z2 are the same. Okay, so those go away. Okay, velocity 1 and velocity 2 are the same by continuity. So this is going to go away. Okay, cool. There is no pump. There is no turbine. And this head loss, for now, we're going to split it up into HF plus H lowercase l. And of course, we're not dealing with those minor losses yet. So this is going to go away. Okay, so we end up with P1 over gamma equals, if we can just kind of erase that, if we can properly erase that. That sounds so British. All my proper stuff equals P2 over gamma plus HF. Yeesh. Okay. We've got 3 unknowns, P1 and P2 and HF. So this is not a lot of help. Not much help. Okay. Especially because what we're looking for is Q. We want Q or we want V. Okay. If we have V, we can get Q by continuity. Okay. So let's keep continuity kind of, in our thoughts. Okay. Because it may come up. Okay. So, okay. Well, what about this though? We do know what this number is, right? So if I plug in 6 meters right here, okay, that tells me something about the difference in pressure between 1 and 2, but it's not really helping me solve for the velocity. However, HF, okay, equals FL on D, V squared on 2G. Now we're getting somewhere, right? Now we're thinking about how to solve this problem, okay? Because notice, this has a lot of things that maybe we don't know yet, but maybe we could get at, right? So right here, we see this nice equation, and it kind of has what we're looking for, okay? It has V, okay? Because if we have V, then we can find Q, okay, from continuity. Okay, so let's not lose track of continuity. The problem with this equation is we don't have F, okay? So, I mean, to kind of give you a taste of how we might drive at that, I could rearrange this equation to make V a function of F. So I could rearrange this such that we ended up with V equals the square root of 2GD HF on FL, okay? And what you can see here, and this is going to be our first equation that's going to be very important in this problem. But what we can see right here is we don't have f. So if we don't have f, we can't get v. Can you say, oh, well, isn't that what Moody's for? Like, didn't we go over to Moody and didn't we use Moody just like on the last problem? Like, we did some things and we were able to figure it out. Well, let's go and stare at Moody and see what happens if we stare at this Moody diagram. So I'm trying to kind of, get your brain wrapped around what the problem is here. Okay, so the first thing is the relative roughness. Okay, so this thing over here, epsilon. Okay, so let's see if we can get at epsilon. Okay, it's Ks over D. The Ks is 0.3, 0.003 meters. And the diameter is 0.3 meters. Okay, so if we divide those, we get 0.001 meters. Okay, so that's pretty helpful, right? So that tells us 0.01 meters, 0.01 meters. Okay, so that tells us that we are somewhere right in here, and I'm going to make this a color that's going to show up. Okay, so let's go ahead and trace that line as best we can. Okay, because that's it's nice when we're actually on a line and we don't have to quite guess quite as much. Okay, so we're going to come up like this. Boom. Okay, so all right, so that's cool. All right, so here we are. But what about the Reynolds number? Okay, so now if we know the Reynolds number, if I knew the Reynolds number was 10 to the 6th, then I could just go up here, hit that line, take a left, and boom, there's my friction factor, right? I could do that. The problem is I don't know my Reynolds number, and you'll notice, as you kind of should know at this point, is that the Reynolds number is a function of the velocity, right? So that means this is problematic, okay? So let's see what we can do about that. Okay, so the Reynolds number equals VD on nu. And for this problem, that's V times the diameter, 0.3 meters, divided by the viscosity, which is 1.13 times 10 to the minus 6th meters squared per second. So that's going to yield, let's just put it right down here, because this is going to be an important equation, 2.65, we'll put one more sig fig, it's completely unnecessary at this point, times 10 to the 5th, okay, and it's got units of seconds per meter times the velocity, okay, and this is equation 2, okay, and you'll understand in a second why I'm putting it in this form. In fact, I'm going to go back over here and do the same for this one. I'm just going to pause it and have it pop up. Okay, so we end up with this equation right here. And again, you're going to see in a second, so here I include my units, which most of you will probably not do. But here we have our second equation. And so the strategy here is unusual, right? Because I can't solve either 1 or 2. Okay, I can't solve equation 2 over here because I don't know V, which of course is the whole point of the whole problem. I want to solve for V. But if I knew V, right, then I could solve for the Reynolds number. If I knew the Reynolds number, then I could plug it into Moody and that would give me F. Okay, well, all right. But the problem is I don't, like, it's just, there's kind of like almost this like circular logic, because you could go back to 1 and say, well, if I knew F, like if I can go back to 1 and I could say, well, if I knew F, then I could get V. And if I could get V from 1, then I could go to 2 and I could get the Reynolds number. If I had the Reynolds number, then I could go up to the Moody diagram and I could get the friction factor. So it's almost like this circular like logic. And in fact, that is exactly the way we're going to solve this, is with this totally annoying circular logic. Okay, so we're going to iterate this problem. So I'm going to do this slowly. I'm not going to like skip anything. And it's not something that we like very much when we first do this. But it's just the way it is. Okay, so what we're going to do is we're going to assume a value for F. Okay, now our assumption is probably going to be wrong. Okay, so you just need to deal with that. Okay, and what we're going to do is we're going to assume a value of F. Okay, and then we will use that value of F in the first equation to solve for V. Okay, so that's going to go right here. Okay, we will take that value of V and we will plug it in over here and we will get a Reynolds number, which is going to go right here. Okay, once we get a Reynolds number, we will go to Moody and we will get a better guess for F. Once we have a better guess for F, we're going to plug it in to the first equation, and that will give us an F value right here. Okay? Now, this is going to stress you out because this first box right here, you have to assume. Okay, you have to make that guess. I'm not going to make it for you. There's no right or wrong answer, and you're already maybe sweating a little bit. We're engineers. We like to have these, like, how am I going to choose this guess? And some of you are going back to the last thing. You're saying, well, can I just use this equation? Okay, you can, but here's the easy way. Okay, I'm going to show you the easy way. And the easy way is this. We go up here, and, well, first of all, if you knew nothing else, I would recommend you choose a number between 0. However many zeros that is, 1, and 0.05. Okay, so I would pick the average value. Maybe I'd pick this one. Okay, if I knew nothing else. Okay, not that value for the relative roughness, but I would take that number and I would follow it all the way to the left and get onto the left-hand side. So maybe I'd go halfway between this value and I would just say, oh, well, let's choose 0.02 or 0.025. Okay, whatever. Okay, those guesses would be perfectly fine. What I'm going to suggest you do, though, in this problem, a more educated guess, would be, well, we know the relative roughness, so let's instead, the most common F for that relative roughness is if we follow this line, and I'm going to do this with a ruler, so if we follow this line like this, okay, and that's going to be your best guess right there. Okay? Now, it doesn't have to be perfect, and the other thing I recommend is that's probably not going to be the correct answer, so what we do is we just pick the easiest number we want to work with. We want 2 significant digits on our answers over here, okay? So we're not going to get it right on the first guess, so what I'm going to do is I'm just going to make my first guess 0.04, because I don't feel like dealing with 0.038. Okay, it's probably a better guess, but I don't really care. Okay, and that's the thing. I want you to realize that it doesn't matter. 0.040 is a nice guess because it's fairly easy to plug into the calculator. And it doesn't matter, we're smart enough to be able to work with, whatever it is we want to work with. But in this case, that's just the way it is. So what I'm going to do is I'm going to take that number and I'm going to plug it in right here, okay, into this equation. And what's going to come out, if I plug that in, is I'm going to get, so from 1, I'm going to get 1.715 meters per second. Okay, and here I think hopefully you're seeing the reason that I wrote it out like this, the reason I did this equation like this, is because we may have to do this multiple times. Okay, so the simplest that you can write this, of V as a function of F, okay, the easier it's going to work out for you. Okay, and so that's why this is in this form, okay, because if I have V, I just multiply it by this number and boom, I got it, right? So I'm going to take this value of V, I'm going to plug it in up there, and that's going to come back out, and that's going to give me a Reynolds number. And the Reynolds number that we solve for is 4.6 times 10 to the 5th, okay? Now, again, we're going to use 2 significant digits in Reynolds numbers because hopefully you can see that when we go up to the Moody diagram, it's not really going to make a lick of difference, what the third significant digit is. So we're going to go up here. So we'll go to 10 to the 5th. Here's 10 to the 5th. Okay, here's 4, here's 5. So 4.6 is somewhere in there, and obviously we're not going to be perfect. Okay, so we're going to scroll this thing all the way up. If I could, just get this to balance right on my lap. And, well, what do you know? Okay, we're like right in that range. Okay, so if I follow that to the left, I'm going to end up at that value that we had earlier, which was 0.03, okay, or 0.038 is what it looks like. Okay, so this is going to be 0.038. Okay, and so we're going to go down here now. I'm going to plug that in, 0.038. Okay, And what we're basically doing at this point, okay, these numbers are pretty close to each other. So probably what's going to happen is there's not really going to be much of a change. So what I'm going to do is I'm going to plug that one into this equation. And we end up with a velocity of 1.760 meters per second. Okay, so that's, I plug that in and then it comes back out. Okay, I'm going to plug this one into equation 2. Okay, and we're going to get 4.7 times 10 to the 5th. And right here, you can already see the Reynolds numbers are very close to each other. But what I'm going to do is I'm going to plug the Reynolds number, this Reynolds number, into Moody. And what you're going to see is that if we go up to Moody, they're so close together that we can't tell the difference. Okay, so like if I go up here under this thing and I'm staring at this and I'm going, okay, well, here's 4 and here's 5 and there's 4.6 and here's 4.7. So close to that one, that basically I'm landing right next to it, still on the flat side. Okay, it's still in this kind of flat area of the graph. So I'm not really going to be able to tell the difference. So when I turn and I go this way, I'm going to end up getting that 0.038. Okay, so here we go, 0.038. Okay, so that means that we've solved it. Okay, because we got the same value twice. Okay, obviously if we were to plug f in again, we would get the exact same. We would get another row of the exact same thing. Okay, so we're not done with this problem because the question, if we remember all the way back to the beginning, was to find q. Okay, so this is our velocity right here, and we want to know q. Now, luckily, this at this point is a fairly straightforward, 1.760 meters per second times pi times 0.3 meters squared over 4. Okay, so q equals whatever that comes to, 0.124 cubic meters per second. Okay, and that's how you solve it. Now, I want to make a few kind of side points here, just a note. When I was taught this in undergrad, no one taught me to start by assuming f. I always kind of did this on my own, and you could start this iterative process anywhere you wanted. Like you could start by assuming a Reynolds number, plugging that into Moody. Like you could have started here. This could have been your first step. Okay, then you could have used that to do Moody. You could have used that to get your f. And then you could have gone to V, fourth, and then you could have just kept on going around the circle that way. You can start this thing wherever you want. Now, what I didn't realize until I was teaching this is that starting with F is the easiest way, okay? And I think the reason for that is if we look at this diagram here, the range of values for F is fairly small, and the guesses are actually pretty straightforward, okay? If you find your epsilon, then your guess for your friction factor. So if this is your epsilon, your guess for your friction factor is right here, okay? And that means your guesses are going to be pretty close. Okay, now you might say, well, what if my guess is really, really, really wrong? And unfortunately, I don't have an Excel sheet to show you this, but I've done this before where I put in a really terrible first guess, like this exact problem. If I put in for my F, if I put in like 100, okay, clearly a terrible guess. And what ends up happening is you have to do this once or twice or 3 times, but usually you will converge on a solution by the third row. Okay, if you're doing it, unless you're screwing something up, like if you go between here and here and you put something in the calculator wrong, well, you just backed yourself up, right? So that's going to be a problem. The other things I'm going to recommend before we move forward is that this is very time consuming. Okay, this requires a lot of time. So this will show up on the final. Okay, if you are running low on time, what you do is this. Okay, and I'm going to highlight this in yellow. Okay, if depending on how much time you have, you solve for this one, this equation. You solve for this equation. You set this up. Okay, you don't do this. Usually this is worth like 2 points out of the 10 points of the problem. Okay, this will probably be worth 2 points. This will probably be worth 2 points or something. I don't know. I'm making up numbers right now. And this will be worth 2 points. Okay, so because this requires so much time, skip this part. Okay, and just go, I don't have time, but say, I'm going to assume that V equals 1 meters per second, and then show me that you know what to do with it once you have that number, and do this part with that assumed V, right? I'll give you these 2 points. I'll give you these 2 points, I'll give you those 2 points, whatever other points, maybe this, I don't know. You'll get all the points, but the points that actually count for doing this, which, maybe it's 2 to 4 points out of the problem, okay? Usually it's not that many. I think maybe it's 3. I don't know, we have to look at it. But, I do want you to learn how to do it, but it is time consuming on a test. So don't stress out too much. If you're running out of time, skip this, okay? That's my recommendation. Okay, now that I made a complete mess of this mockery of a problem, let's move on to the third one. Okay, so as just kind of a final reminder, as we finish up with this problem, this is a type 2 problem, okay? And so this is how you're going to want to, assuming it's not all written all over it, but this is how you're going to want to solve it, how you're going to want to iterate to deal with it. And the principal thing here is that, based on what's given, what makes this kind of a type 2 is that we know one of the values here and we don't know the other, okay? Now, the last thing that I want to accentuate is that this equation 1 is going to change from problem to problem, okay? But the key is that it's going to be v as a function of f, okay? And type 2 will be Reynolds number, the second equation will be Reynolds number as a function of v, okay? And then the third one is just going to be using Moody. It'll be f from Moody, okay? And the equations will change depending on the problem, okay? So, and it won't just be like a different version of this. It could be like a different version of this, but usually what's going to happen is that, however we get at this, or it may not even be from this equation, it's going to be from one of our tools, right? From one of these things, okay? So it's going to be a little bit, it's going to be a little bit tricky, okay? So logically then, that implies that this third one is going to be a type 3, okay? It also implies that, based on what I just said, that when we get to the Moody part, this is going to be a question mark, and this is going to be a question mark, okay? And so that's troubling, okay? I'm going to go ahead and erase those dots just because I don't really need that, okay? So let's go back over here and let's look at this problem, okay? And this is the type of problem that we're kind of training ourselves to do, okay? This is a design problem. Determine the size of a clean wrought iron pipe, okay? And it gives us that sand roughness factor required to convey 4,000 GPM, so we know Q, okay, of oil, so we know the viscosity. Again, this is a viscosity. Over a length of 10,000 feet with 75 feet of head loss. Okay, again, we don't really have a lot to go with. Just to start this off, I'm going to go ahead and convert this 4,000 gallons per minute. Okay, so now we've got that converted into something we can use, okay? And then we're going to kind of start staring at this. And here's the problem, is we know there's a head loss along this pipe, okay? So I'm going to kind of draw the pipe, we know the length of the pipe, and drawing-wise, this isn't really all that different from the last one, 10,000 feet. We don't know this diameter, okay, and that's problematic, okay? We know the flow rate coming in here, 8.93 CFS. Okay, and again, of course, we know the diameter. If we know the flow rate, we know the diameter, we can get a velocity, which is nice, but we don't, right? And so the big problem here with all of this, again, it's kind of the same problems we had last time. If we look at our tools, there's no interesting geometry in this problem. There's no hydrostatics. There's nothing to momentum because there's no forces on moving fluids that we're trying to solve for or that are given or anything. So, and then, continuity will come into this maybe. But, and even the energy equation, if I solve this the same way I did the last one, I'm going to get P1 over gamma equals P2 over gamma plus, the head loss due to friction. So it's almost like we're lining up the exact same equation as last time, with, the energy. So we're just thinking about the head loss over this length, okay? Because that's like a key thing we're given is this. Okay, so we say, okay, well, cool, right? Head loss, I know this is the Darcy-Weisbach equation, v squared onto g. Now the problem here is that, v, I don't know. I don't know v. I don't know this. I don't know this. And I don't know this. So that's awfully frustrating. However, we can do some things that are going to make this a little bit easier on ourselves because we do know Q. So because we know Q, so we'll use a little continuity here. Okay, because we know Q, we know the relationship between V and D. Okay, so kind of up here off the side, I'll say Q equals VA. Q equals V times pi D squared on 4. Okay, which means that V, so V is 4Q over pi D squared. Okay. So I'm just doing that because this means I can kind of get rid of a variable, right? Because if I plug this in over here, then I get F L on D, V squared, well, 1 on 2G, and then V squared becomes 4Q over pi D squared, okay, and V squared is squared. Okay, you're like, oh man, that's getting quite ugly. Okay, if we rearrange that, we're going to get a really ugly equation. Okay, and it's going to be D equals, now, this is nice because D is what we're looking for. Okay, the fifth root, if you count them up, you've got 1 here and you've got 2 here squared, so there's going to be 5 of them. So we take the fifth root and we'll get 8L Q squared F on HF G pi. Oh, that hurts. That smarts. Now you're saying to yourself, like, okay, okay, Wagner, you just kind of jumped the gun here, right? You're telling us this is equation 1, but what's the problem here? Why are we going this crazy route? Like, because here we are, and if we stare at that equation, you just did a lot of algebra, and we still don't know F. Okay, and yeah, and so if we don't know F, how are we going to get D? Okay, and here's kind of the only way to get at F, really, is from the Moody diagram here. And the problem is when you don't know D, we can't get the Reynolds number because that's VD over nu. We also can't get the relative roughness because that's KS on D. Okay? So what we're going to have to do here is we're going to have to assume a D. Okay? So if I assume a D here, I can get the relative roughness. If I assume a D here, that's great, but I still need a velocity, right? Okay, so what we're going to do over here, okay, this is going to be our first equation. Okay, and we're actually going to kind of do this in reverse order, but we're going to assume a D. Okay, and it's kind of exactly what I just described. So we're going to assume a D. That'll give us this relative roughness. Okay, that'll give us a Reynolds number. Okay, then we're going to get an F from a Moody diagram. Okay, we're going to plug that F in over here to give us a better guess for D. Okay, so let's just kind of just keep working in it, and you'll see how it works. Let's make this. Let's plug in some numbers, and then make this kind of a simpler version of 1. So give me 1 second. All right, so rearranging it, we get this pretty easy to work with. We plug in F, we take it to the 1/5, and then we multiply it by 3.8454, because that's equation 1. All right, so we're going to need to kind of get at, the two sides of this Moody, okay? And it doesn't really matter the order that we're going to get into them. Let's go ahead and we'll do the Reynolds number first. Okay, the Reynolds number is VD on nu. Now, the problem here, of course, is V and D depend on each other because one of them has the flow rate. So we are going to make Reynolds number a function of the diameter, okay? Because, we're assuming a diameter in order to solve all this problem. So in order to do that, I'm going to do, in place of Q, in place of V, I'm going to put basically a function of Q. So we did this earlier. So 4Q over pi D squared, okay, times D on nu. Okay, so this ends up being 4QD on pi D nu, and one of those D's is extra. Okay, so let's get rid of this one right here. Okay, so if we plug numbers in, okay, so it equals 1,137,000 feet divided by D. Okay, so the one nice thing about keeping track of your units here is that this tells you that the D has to be entered in feet. Okay, so this is going to be our second equation. Okay, and again, this is just so that I can just take a d and plug it in there, and it'll make it easier. So I need a third equation, and that's going to be for epsilon. Okay, again, these equations are going to change from problem to problem. Okay, so here I'm going to plug in my Ks, which is given. I forgot what it is. Oh, 0.00015 feet divided by d. Okay, so that's pretty straightforward. Okay, so no need to do any fancy math there. Okay, so that's my third equation. Okay, so already, in some way, I'm imagining, this is looking a little confusing, and it is a little confusing. This is a very complicated thing we're doing here. Most people cannot do this. Okay, so what we're going to do is, and I'm going to kind of, I guess I'll do this in white. I think that's how I did it last time. What we're going to do is we're going to assume a d. Okay, again, you could assume something else. But these problems tend to work out pretty well like this. Okay, so, and I'm going to give you some advice for assuming a d that I'm actually not going to follow in this case. But, so you're going to get epsilon. So epsilon and Reynolds number basically happen at the same step. So you can do these in either order. I don't know why I chose to do it this way on the key. It's not important. Okay, Reynolds number from 2. Okay, and you can see that if we assume a d, we can solve this one and we can solve that one. Okay, so once we have an epsilon and a Reynolds number, we can use Moody diagram to get f. Okay, Moody. Okay, once we get a good estimate of f from there, we can plug that into 1 and we can get a d. Okay, and that's going to be from equation 1. Okay, and that's the process. Okay, so now here's what I'm going to recommend. Okay, and if when you assume a d, okay, and I do this with all my classes in person, it's a little bit easier there, but when you're assuming a d, what I recommend you assume is you assume the easiest thing to work with. The easiest number to work with is 1. Okay, obviously, you could assume 0, but then this whole problem goes up, right? The epsilon is infinite, the Reynolds number is infinite, and then you don't overdo it. So the easiest number is 1. Okay, in this case, for whatever reason, I don't know what it is. It may have just been because, I don't know why I chose it, but I chose 1.2 feet. Okay, and it's not going to matter. You may think so, and you're welcome to plug in a different number. Again, I've gone into this and I plugged in 100, and it didn't matter. Okay, so don't stress out too much about it. Just choose an easy number. Choose 1 foot or 1 meter. That's my recommendation to you. Okay, so if I plug that number into 1 up here, I'm going to get 1.25 times 10 to the negative 4th. And actually, we're going to make a point of this here. We're not going to write it like that, okay? For epsilons, it's always easier to write it as 0.000125. Okay, and that's just because of the way they write it up here, okay? So, don't use scientific notation, even though on my key I did. All right, so now I'm going to take that d, I'm going to plug it in right here. And I'm going to get, 1 second. Actually, I'm going to fix an error right here real quick. This has 1 too many zeros, which means this has 1 too many zeros. Okay, and these commas are in the wrong spot. We won't worry about those. Okay, so that's going to change things ever so slightly, but we'll have it correct moving forward. So if we plug this in here, 113,700 divided by d, and if we plug that in, we're going to get 94,750. Okay, this is too many sig figs, but I'm just following my key, so for now that's okay. And what we'll do is we're going to go up to the Moody diagram now, okay, and we've got these two values, okay, so mentally keep track of these two values, okay, so 0.000125 over here, and over here 94,750, okay, and we're going to note that this is too many significant figures. Okay, well, let's zoom in and let's focus on that. 0.00125. So we can see why putting this in scientific notation is not very helpful. We want to find 3 zeros. So this is 3 zeros right here. So this is 1 right here, and this is 2, and this is 1.5. So we're right in there, okay? And that's a little annoying, as you can see, okay, because we have to try to guess where that is. Okay, about roughly a quarter of the way between those two blue lines. Okay, and you're not going to be perfect at this, and that's okay. Okay, now we need 94750. Now this is going to be easiest if we put this in scientific notation. So if we did 9.5 times 10 to the 1, 2, 3, 4, 10 to the 4th, that's going to be much easier. Okay, so this is approximately 1.0 times 10 to the 5th. Okay. Okay, here's 10 to the 5th. Here's 8 times 10 to the 4th, 9 times 10 to the 4th. So we're going to be about right there. Okay, we can see where these things meet more or less. Okay, right in that area. Okay, so now we're going to take our, trusty, dusty ruler, which somehow is affecting my screen. You would think that was impossible. Okay, and we're going to get more or less 0.0018 or 0.018 or 17. Now, actually, what I'm going to do is I'm going to use the number that it looks like it actually should be a little bit higher in there. I'm going to use the number that I did on my key just because. Otherwise, I have to redo all these calculations. But basically, there's a little play, right? It doesn't always come out perfect. So I'm going to use the number that I did on my key. So the number I got on my key was 0.02. Okay, if we get 0.02, then I can go over here to D, and I can plug that 0.02 into equation 1 right here. Okay, and if I plug that in up there, I'm going to get 1.40 feet. Okay, so we note that this number right here and that number are different. So we're going to do another line. So I'm just going to take this number, and I'm going to copy it down right here. Okay, so 1.40. Okay, I'm going to plug that into equation 3. So I'm going to plug that in right there. And I'm going to get, 0.000107. So we have to be feeling pretty good. We're not really that different here. So, things are probably looking okay. So we get 881,214, an awful number. 8.1 times 10 to the 4th is fine. Okay. And then we're going to go up to Moody with these two numbers now. Okay, so I'm going to write these up here so I know what they are. 81,214 on this one, and the epsilon is 0.000107. Okay, so let's go up here. We're going to start with the epsilon, 0.00107. So that's right. Let's just put that right on this line for the most part. Okay, so that's cool. All right, I should be able to trace that fairly well. And once we get into the region we're in, it doesn't really matter. And then we're going to go to like 8 times 10 to the 8.1 times 10 to the 4th. Okay, so that's basically right on 8. So we'll go like right there. Okay. And now if I follow that one over, and again, you can kind of see why it's not that important to be too critically accurate on the first go. It's the second one that's usually going to get it for you. Okay, so that's somewhere in there. Okay, so I'm going to go with, just because I'm following my key, and it's more accuracy than I would expect you guys to get. But my guess is I actually did this with the computer. You can get really accurate with this if you use the computer, which obviously you can't do on the test. But anyway, so if that's what you get, which is pretty close to where we were, then you plug that into equation 1. And what comes out of that is 1.39 feet. Okay, so now we're feeling pretty good. Okay, this is pretty good. Like if you were doing this on a test and you stop here, I'd be okay with it. You're out to the third significant digit. But let's just do this all the way. 1.39 feet. Okay, so if we plug that in, following the same pattern, we get 0.000107. We could probably stop right here, right? Because the numbers are so close, that we're not going to be able to tell the difference here. So this is going to end up being 0.0195. And then if we plug that in to the first equation, we're going to get the same thing. So this is the size of the pipe. Okay, so, you know, because this and this are the same. So now you're good. Okay, so that means D equals 1.39 feet equals 16.68 inches. Okay, now they don't make pipe, not available. Okay, they don't make pipes in that size. So you need to go one up, and you go to 18 inches is the size you would use if you would order, if you're ordering this pipe. Okay, an 18-inch pipe will get you more than 4,000 gallons per minute of oil with that amount of head loss. Or another way to think of it is if you have that 18-inch pipe, you will get less than 75 feet of head loss to deliver that much. There's a lot of reasons why you just want a bigger pipe, right? It's, you know, bigger pipes are definitely helpful, you know, for head loss and more flow rate. So, all right, so that's it. These are the 3 types. These are brutal. For homework, I'm only going to assign one of these 3 types. So you need to be careful and make sure that you work all 3 types. Okay. So here's those 3 types. You know, one where you just don't know the head loss, the friction loss. And then the other 2 where you're asking for Q, which you're saying like, how much flow rate will this system carry? And these searching, and the last one, the diameter. This is the beastly one. Okay, it's not actually that much harder than 2, but it does have an extra calculation per iteration. So that's it. I guess we're under an hour, so I hope you're having a good day. Please ask me questions and, you know, work through the homeworks on this, because I don't want to sugarcoat this. This is hard. Anyway, so thanks, guys. And again, take care of yourself mentally, physically, emotionally. All that is way more important than any of the schoolwork. If I can help you in any way, please let me know. All right, take it easy. Okay, good night.